Okay, hello. Today the question I chose was the sum is right. Inside this question, we have suppose that we generate x1 to xn, which follow the uniform distribution, and they're independently and identically distributed. Let u be the minimum of this and v be the maximum of that. Compute the probability that u plus v is greater than 1. Honestly, the minute I see this question, the first thought is probably I need to take the integral and then go from there. But there's actually a very unique trick to this question that doesn't require um, calculating too much integrals or anything. Basically, the idea is actually to use symmetry. So the minute we see that there's this minimum and maximum of this thing, we can define a second variable called y, and y would just be the 1 minus x respectively. And because x follows this distribution, y should also follow this distribution because 1 minus that would still fall within the range of 0 and 1 and would still be uniform. Okay, once we establish this fact, then we can kind of go with looking at the distribution of y. So the minimum of y will be 1 minus the maximum of x. So it'll be kind of like this relationship. And then the same way goes the other way around. So then the maximum y would be 1 minus the minimum of x. Same thing. So then we can set up the probability that we want to find pu plus v is greater than 1. So we can express this in terms of y variable. So in terms of this, it would just be 1 minus x, 1 minus maximum of y plus 1 minus minimum of y is greater than 1. So we sort of just rearrange this inequality, and we can in fact get that the minimum plus the maximum is smaller than 1. So then this basically means that we just partition the probability into two halves, either smaller than or greater than. And this is everything that it could. And it could also be equal. But we know that in the what is it called? In the distribution density thing, the any at any just specific point when it equals, the probability is 0. So then hence the left-hand side equals the right-hand side. So then that means that each of them are one half in probability. So this is just basically using a really good symmetry property to actually simplify with this y variable. And the most typical way of doing approaching these type of questions, if there wasn't such a symmetry, would be sort of just to write out the actual equation and see where that takes us. So for an instance, we have an independent variable uniform. Their joint PDF is built on this logic. So we have one of them must land at the minimum, so we call that U. The other must have landed at the maximum, which we call V, and everything else is in between this. So then there are n ways to choose U and V because we have n independent variables, right? And then the rest has to fall between. So we have V minus U, and then there are n minus 2 of them. So that's how we get the PDF is this. And obviously U and V have to fall between 0 and 1. So next what we want to do is we want to find the probability over the specific region. So we kind of set up a double integral that sums up the U and sums up the V. And we have to find the boundary, which are the limits. So we have a lower bound for U, the condition that U plus V is greater than 1. So we just rearrange this and we get U is greater than 1 minus V. And then there is a upper bound for U because in the order statistics, U must be less than V, so U is smaller than V. So that was already a given condition. And then bounds for V. For U to exist between 1 minus V and V, it must be true that 1 minus V is smaller than V. So solving this gives V is greater than 1 half, so the maximum of V is 1. That's pretty straightforward, I'd say. So the integration bounds, V goes from 1 half to 1, U goes from 1 minus V to V. I'd say I think I can kind of see it as like, um, this equation is straightforward because we just go from what we're given. This one is pretty straightforward as well. I think it's only this last condition that is kind of a little difficult, but I think it's definitely possible to re reason because you kind of have to know um since u has to be greater than 1 minus v, but you can't be that. So that's kind of the bounds of v, u. And then since you have 1 minus v is smaller than v, then you just kind of rearrange that and you get the v boundaries. So these are the boundaries. And then you just evaluate the integral. You just write the probability of this is just the double integral of the bounds we just found, the PDF that we just found earlier, du dv, and then you just evaluate this integral, power rule, antiderivative, pretty straightforward. You get to this point, then you take the outer integral, substitute it, kind of evaluate it, and we still get 1/2 of what we expect. So basically the idea of this question, the second way is definitely the like the normal approach of just like we have the probability, we're trying to find this. So we're gonna break it down into finding the PDF. And then once we find the PDF, we establish the bounds and then it's a standard double integral. But I think a better way, because this question was kind of hard, I think the major thing that was hard to realize was just setting up this y variable and using the symmetry property. Okay, that's enough here.